Good morning, sir. Good afternoon, sir. This is my first topic, design of tension members. And this is my report, first report. Mode of failure, gross section yielding, net section yielding, block shear failure. Design of strength of member is at least of strength due to yielding of gross section, rupture of critical section, block shear. Now, A. Sa design strength due to yielding of gross section is the design strength of members under axial tension or TDG is equal, monetary equation, TDG is equal to Fi AJ over MO, where YMMO is equal to 1.1. Then design strength due to rupture of critical section plates, the design strength in tension of a plate TDN or TDN is equal to 0.9 FOEN over M1, and M1 is equal to 1.25, and EN is B minus ND plus summation of P2 PG, basa na, and mo iyang forma sa isang figure. Then sa angle bolt kana siya man siya ang idang kuan with angle with single leg connection. Then the formula is BS is equal to W plus W sub 1 minus T, and BS equal to W. Then net section rupture and threaded rods. TDN, T sub DN is equal to 0.9 FOAN over M1. And EN is equal to net throat area of threaded section. Net section rupture and single angles. TDN, T sub DN is equal to 0.9 FU and A and C over M1 plus beta A sub GO and FY over MO, where beta is equal to 1.4 minus 0.76 times W over T times FU over Fy, and BS times BS over L is greater than, it's lesser than Fy MO over Fy M1, and is lesser than 0.7 and tension members mana. And for primary sizing, the rupture strength of net section may be approximately taken as T sub Dn is equal to alpha A times En Fu over M, mana sa kanong ang reference. Then block shear failure, mana mga pictures, kini siya. Angle, gusset plate, then ang bolts kana, and then ang section kini na siya. Next, block shear failure is also seen in welded connection, and a type failure of gusset in the welded connection is shown in the figure. Kana siya nga figure. Balik. Short angle used to connect the gusset and outstanding leg of the main member as shown in the figure. Kana. Then determine sample problem. So ano may labot yung sample problem. Para sa pagkuha sa gross area, the tension member is sa step 1, pagkuha sa gross area, the tension member is obtained assuming that the section fed at yielding using equation AJ is equal to 1.1 times TDJ over Fy. Then step 2, taking into consideration reduction into the area due to holes and assuming efficiency in 85%. Area is increased by 15 to 20%. Then assume gross area is equal to 1.15 times AJ, then memory required. For welded connection, gross area is taken as same as required. Step 3, tile section is chosen by steel table by gross area. And step 4, now strength of the section is checked as per IS code. Now check as IS code for 800 by 2000 section 6. Design strength due to yielding of gross section. The design strength of members under axial tension is T T sub dg, or ang gagdang formula is T sub dg is equal to Fy times Ag over MO, where MO is equal to 1.1. And the design strength due to rupture of critical section is plate. The design strength in tension of plate is Tdn is equal to 0.9 FOEN times excuse me, center of tension plate TDN is equal to 0.9 FOEN over M1 times M1 is equal to 1.25. May value sa MY, where EN is equal to B minus EN. Nakadikta namin natin ha. Then our next topic is and design strength due to block shear. The block shear strength is T dV of connection shall be taken as the smaller of T sub dB is equal to A average Fy, ang A ang average is the BG, Fy over square root of 3 ba na pagbasa ana MO, or R plus 0.9 FU ATN over Y1, or 0.9 FU and FU times ABN over square root of 3 M1 plus Fy A sub TJ over MO. Muna isang forma sa plate. Then step 5. After checking design strength is less or too much in excess, a second trial is selected and all design processes are repeated. And step 6, slender ratio is also checked. It should be less than 350 for tension member. And slide show sa second report. My second report is bending stress. Beams are bending stress in beams. Beams are subjected to bending moment and shear forces which vary from section to section. To resist the bending moment and shearing force, the beam section develops stresses. Bending is actually associated with shear. However, for simplicity, we neglect effect of shear and consider moment alone. This is true when the maximum bending moment is considered shear is 0. To find the stress due to bending, such as theory wherein stress due to bending alone is considered known as pure bending or simple bending theory. Now, for example, of pure bending, kana siya. Ang ilan ang pagkuhan sa equation. Na saging na mo bend, which is dire natural axis, and muna mo bend sa center. Then excuse me, pause. Sagging or fibers below the neutral axis in a get stretch, or fibers under tension. Fibers above the NA get compressed, or fibers are in compression. Hugging or vice versa. In between there is a fiber or layer which neither undergoes tension nor compression. This layer is called neutral layer, or stress are 0. The trace of this layer on the CS is called the neutral axis. Assumption made in pure bending theory. The beam is initially straight and every layer is free to expand or contract. The material is homogeneous and isotropic. Young modulus E is same in both tension and compression. Stresses are within the elastic limit. The radius of curvature of the beam is very large in compression of the depth of the beam. In a transverse section of the beam which is plane before bending will remain plane after bending. Stress is purely longitudinal. Yes. Relationship between bending stress and radius of curvature. Now, consider the beam of section length of dx subjected to pure bending. After bending, the fiber AB is shortened into length, whereas the fiber CD is increased in length. In B over W where there is fiber EF which is neither shortened in length nor increased in length or neutral layer. Let the radius of fiber EF be R, let be R. Let us select one more fiber GS at distance of Y from the fiber EF as shown in the figure. So, EF is equal to E prime F prime is equal to dx or is equal to R the diameter. The initial length of fiber GS is equal to R D. After bending the length of GS equal to, so GS equal to R plus Y D times D or is equal to R D plus Y diameter. Change in length of fiber. GH is equal to R diameter plus Y diameter minus D. R diameter is equal to Y diameter. Therefore, the strength in fiber GH or E change in length, original length, and is equal to Y dE, Y over RDO, and what's that? Sigma is, di na sigma. I don't know. E is equal to Y over R. If stress is the bending stress, and E is the Young modulus of material, then strain is equal to stress over E or modulus, whereas stress B over E is equal to Y over R is equal or greater than stress B over is equal to E over R times Y, whereas stress B is equal to E over R, Y is equal to EI bending stress in fiber is proportional to the distance of the fiber from the neutral axis, and hence maximum bending stress occurs at the fiber's farthest fiber from the neutral axis. Note, neutral axis coincide within the horizontal central axis of the cross section. Kana. Nasa to nga. One moment of resistance. One of the neutral axis there are compressive stress, on the other there are tensile stress. This stress from a couple whose moment must be equal to the external moment M. Then the moment of this couple which resists the external bending moment is known as moment of resistance. Nasa sa babaw na. Sa kini ang ilang neutral din sa babaw. Consider an element area dA at a distance of Y from the neutral axis, kini neutral axis. The force of this element area is equal to stress times dA, where is equal to E over R Y times dA from 1 kini. The moment of this resisting force about neutral axis is equal to E over R times Y dA times Y is equal to E over R Y squared dA. Total moment of resistance offered by the beam section. M sub 1 is equal to summation of ER, it's not summation, integral of E over R times Y squared dA is equal to E over R integral of Y squared dA. Integral of Y squared dA is equal to second moment of the area or moment inertia about the neutral axis. Therefore, M prime is equal to E over R times I over I sub in A. For equilibrium moment of resistance, M prime should be equal to applied moment M. So M prime is equal to M. Hence we get M is equal to E over R times I sub in A. So for equation 1 and 2, muna na mabuo. M combine M over I in A is equal to E over R is equal to stress over Y, bending equation of Bernoulli-Euler bending equation, where E is Young modulus, R is radius of curvature, and M is bending moment at the section, where I is moment inertia about neutral axis O. And Q is a bending stress, bending stress, and Y is distance from fiber from the neutral axis. section of modulus, say, M is equal to bending stress over Y, or bending stress is equal to M over Y, or M over I times Y. It shows maximum bending stress occurs at the greatest distance from the neutral axis. Let Y sub max equal to distance of the stress fiber from the NA. And bending stress max, maximum bending at distance Y max. And so it is equal to bending stress is equal to MI Y, which is maximum, where M is the maximum moment carrying capacity of the section. So M is equal to bending stress max times Y over Y max. So M is equal to bending stress max times Y over Y max is equal to bending stress max of Z, where Z is equal to I over Y max is equal to section modulus property of the section. The unit is cubic millimeter or cubic meter. Section of modulus or rectangular cross section. Mana? Sa P din Y max. So Z is equal to modulus over Y max, or is equal to BD cube over 12 over D over 2. And is equal to BD squared over 6. Hollow rectangular section, mana? Kini siya, which is Z is equal to modulus over Y max is equal to 1 over 12 times BD cube minus BD cube katong gamay is equal to D over 2. Kaya sa halo ning gamay, or is equal to, kung ato simplify, BD cube nga dako and over minus BD cube nga gamay over 6D. Now, for circular section, Y max is equal to D over 2 mana. So ang formula is Z is equal to modulus section over Y max is equal to pi D to the 4 over 64 over D squared, or pi D cube over 32. For triangular section, kana ayang ng neutral axis, which is Y max is equal to 2h over 3. So G is equal to modulus section over Y max, so it's equal to BH cube over 36 over 2h 2/3 times h, so it's equal to, so simplify, BH squared over 24. So next, excuse me, our third topic is about stress. Stress in beam, stress induced by shear force at section and beam may be analyzed as follow. Consider the element of length of beam between the section AA and BB separated by a distance dx as shown in the following figure. Let the moment acting at AA and BB be M and M positive and DN respectively. Let CDB fiber at thickness of at distance y from the neutral axis. Then the bending stress at left side of the fiber CD is equal to M Y over I. Mana siya? Figure niya. For the left side of the layer, CD is equal to my over b dy. So, and force on the right side of layer CD is equal to m plus dm times yb dy over y. Therefore, unbalanced force toward right in the layer CD is dm times y times b times dy over I. There are a number of such elements above the section CD. Hence, unbalanced horizontal force above the section CD is equal to the integral of dm, ano siya nga formula. Then the horizontal force is resisted by the resisting force provided by the shearing stress acting horizontally on the plane at CD. So, let the intensity of shear stress by T equating the resisting force provided by the shearing stress to the unbalanced horizontal force. So, we have, muna ilang formula, TBdx equal to kini, then or pwede na kini. So for the left side of the CD is equal to my over b dy. So and for the right side of the letter CD is nabalik ni. Excuse me, balik ni. Mana ang formula niya. Then but the term dm over dx is equal to f, then the therefore substituting in the expression for t, we obtain t is equal to f ay over ib, where f is a shear force at section and beam, and a are area above or below fiber shaded area, and y are is equal to distance from NA to the center of the shaded area, and I is equal to mi of the entire section about the NA. Then b is the breadth of the fiber. Note the above expression is for horizontal shear stress from the principle of complementary shear. This horizontal shear stress is accompanied by vertical shear stress of the same intensity. Then shear stress variation across a few standard cross section. Rectangular section. Consider a rectangular section with B and depth D subjected to shearing force F. Let AA be a fire at a distance y from the neutral axis as shown in the figure. From the equation for shear stress, T is equal to F AY over IB, where A is equal to times D squared times Y. Then, mana ang formula pagkakuan. Then, thus the shear stress variation is parabolic when I at, muna ang siyang formula, kanina, manana. For a circular section, consider a circular section of diameter D as shown in figure. Let A be a fiber at vertical distance y and an angle theta from NA in which shear stress is to be determined to find a moment area above the fiber AA. About the NA, consider an element thickness dz at vertical distance z from the NA. Let the angular distance of element be theta as shown in the figure. Kana. The area of the element A is equal to B dz. Kana na figure. With the element of B is equal to D cosine theta. Next. And Z is equal to D over 2 sine theta, or 2 dz, or D over D theta is equal to D over 2 cosine theta. So, the area, so ang sum up is A is equal to D cosine theta times D over 2 times cosine theta d theta is equal to D squared cosine squared theta d theta over 2. Moment area of the element about the NA is equal to area times Z. So, D squared over 2 cosine squared theta times D squared sin theta is equal to D cube over 4 cosine squared theta sin theta d theta. Therefore, moment of the entire area above the fiber AA about the NA is equal to AY. So, mana pagkas formula. Moment of inertia of the section I is equal to pi d to the power 4 over 64. Though substituting in the expression for shear stress such that T is equal to F AY over IB. So, shear is equal to F, then D cube over 12 cosine cube theta is equal to 16 over 3 times F over pi D squared cosine theta cosine squared theta. Then is equal to 16 over 3 times F over pi D squared times 1 minus sin squared theta, where B with the fiber A is equal to double A is equal to D cosine theta. So 16F over 3 pi D squared times 1 minus y over D squared to the power of 2. Hence, shear stress varies parabolically over the depth. Its value is 0 at the extreme fibers, where y is equal to D squared and its value is maximum when y is equal to 0 at the NA, and is given by shear max is equal to 163 pi f d squared, or is equal to 4f over 3 pi d squared over 4, where is equal to 4f is equal to 3a. So F is a shear force and E is the area section and area cross section, and is equal to average shear stress. Thus, in circular section, shear stress is maximum at the centre and is equal to 4/3 times the average shear stress. So sa isosceles triangle section, ano siya? Let A be a fiber distance from the top. Shear stress in general, ano eh? Maora man na. Our last topic is column under centric load. So, let's suppose a load acts on a column of distance A from a plastic centered ES shown in figure, mani. Kanang figure. Now, when A in the area of compressive steel, A sub 1 is area of compressive steel, and ES is equal to area of tensile, and Fs is equal to stress in tensile steel, and Fs sub 1 is equal to stress on compressive steel, and T is a tensile force in steel, and Ce is equal to compressive force in concrete, and Cg, what's this? Cg is compressive force in steel, where Ce is equal to 0.5 if A sub 1 BA, and Cg is equal to ES Fs, and T is equal to ES Fs. Now, Pn is equal to Ce plus Cg minus T. So, Pn is equal to 0.85 if A BA plus AS sub 1 EF times EF sub 1 is equal to ES Fs, so on and so forth. So, equation is called load equation. To find out moment carrying capacity of the column, we take moment about plastic centroid. Kana. So, Pn over theta is equal times E is equal to Mn is equal to C H minus Ce H squared minus E squared plus Ce times H squared minus D sub 1 plus T times D minus H squared, where let D sub 2 is equal to H over 2 minus D sub 1, and is equal to D minus D sub 1 over 2, and E sub 1 is equal to D sub 2 plus E. Considering moment about center load of tension steel, so PU is over theta times E sub 1 is equal to Mn is equal to Ce D minus A over 2 plus Ce is equal to times D minus D sub 1. Now, considering a moment about plastic center in terms of D sub 2. Shit. Next. Now. Now, Pn times A is equal to Mn is equal to Ce. So, D minus D sub 2 minus A over 2 is equal to Cs times D minus D sub 2 minus D sub 1 plus T times D sub 2, where Mn is equal to 0.85 Fc BA, dE is equal to D sub 2 minus A over 2 plus ES sub 1 times Fs sub 1 times D minus D sub 2 is equal to E sub 1 plus ES times D sub 2. Ano yun sa formula? This equation is called moment equation. Then, case pure axial load crushing failure. We know that Pn is equal to Ca plus Cg minus T, but in this case there is a pure compression. So no tension still is present. So En is equal to Es plus Es sub 1, and Cg is equal to C1 plus C2. So Pn is equal to 0.5 Fc sub 1 and AC plus EST Fy. And Pn is equal to 0.85 Fc sub 1 times Ag minus A sub 1 plus EST Fy. So, the formula is Pn is equal to 0.5 F sub 1 Ag plus Fy minus 0.5 F sub 1 times EDS. So, muna load equation, then moment equation is equal to 0. For balance, first we need to find a figure. So, if we want to express in terms, next. Now, using A is equal to 100 or MPa and rearrange, so if CB is equal to 600D minus 600CB. So as at is for balance failure, muna sa mga formula. So for filial failure, in this case, no axial load is acting on the column and column just behave like beam. Therefore, PU is equal to 0. In figure comparing ABC and ACB, we get 0.3. So, mana ang formula. So, in equation, value of A cannot be found at because even though we know that but we don't know the exact value of so whereas the case of balance failure, A could be found as an equation involved rather than A. So now, now P ang load equation is Pn is equal to 0.5 Fc BA plus ES minus FH. So So, thank you, mana to.